Hello everyone, engineering statistics and linear algebra. Today we do discuss two important concepts, that is a basis and a echelon form of a matrix. These two are essential to understand a null space and column space of a matrix in a use. A basis. A basis is a set of vectors that generates all elements of the vector space, and vectors in this set are linearly independent. Let V be a subspace of n space for any values of n. A collection B, that is equals to vector v1, v2 and so on vr of vectors from V, is said to be a basis for V if B is linearly independent and spans of V. Let us explain these three statements with the proper examples. Consider uh, a set of vectors V. It has vectors v1, v2, v3 and so on vn. They all are in a space of Rn. Out of these vectors, consider the one more set B. Only few vectors are considered here, v1, v2 till vr, not till vn. Only vectors from v1 to vr are considered. They do belong to a set of vector v. If a collection of vector b is said to be a basis for this vector v, it is said to be a set of vectors for this set of vectors v. The first condition is all these vectors are linearly independent and they are spans of v. Meaning of span is a linear combinations of v. If these two conditions are satisfied, this set of vectors, then you can say that all these vectors are basis for a vector set v. Alright, so if any one of the condition is not satisfied among these two, if any one of the condition is not satisfied, then you cannot say that basis for v is b. Alright, so there are two possibilities in a vector set. Vectors v1, v2, v3 till vm, they can be either dependent or independent. So if these vectors are dependent, v1, v2, v3 and so on till vn, if these vectors are dependent, then basis will be lesser than its column number of columns. We'll come to know. So the next is, the one more possibility is all these vectors can be independent. Then so you can say that number of bases is equals to value of its column. Okay, consider one example. 1 2 3 vector 1, 2 4 6 vector 2, 3 0 0 vector number 3. Here the vector v means a set v is considered, where it has v1, v2 and v3. Okay, this is done here. Then consider the one more set, that is b. They are a part of this v1, v2, v3, and if some vectors are written here in this set, if you want to say that they are basis for this v, they should satisfy two conditions. They are linearly independent and they should have a linear combinations of v. Okay, so vector 2 can be represented using vector 1, so that these two vectors are linearly dependent, and What about vector number 3? Here none of the vector is used to represent a vector number 3. So that vector v3 and only vector v1 are the basis for this set of vectors v. Out of three vectors, we have considered only two vectors. These two are linearly independent, and linear combinations of these two vectors will fall in the span of this vector. Consider the one more example. Consider one more example here. Consider one more example. Okay. So 1 0 0 first vector, 0 1 0 second vector, 0 0 1 a third vector. Then find the basis for this vector. Can I write basis for this vector is v1, v2 or v3? All these three vectors are the basis for this vector v, because 2 cannot be represented using 1, 3 cannot be represented using 1 and 2, and 1 cannot be represented using 2 and 3. All are independent. All these vectors are independent. So that the basis for this vector is all these three. So that I have said here. So if vectors are independent, then they do have a right set. If the vectors are dependent, then a basis for the vector will be lesser than its column. The column number is 3 here. So the basis for this vector is equals to 3 because they are independent. So these are the concept of basis. Let us see some examples. A collection Ij is a basis for Rn since it spans Rn and the vector I and j are linearly independent. This is called the standard basis for n dimensions R. Similarly, Ijk is the standard basis for R3. Consider a xy plane here. Xy plane, so it is called as R2, and unit vector I along x-axis, a unit vector j along y-axis. Always I and j are spans, are the basis for this R, because they are always linearly independent. I cannot be represented using j cannot be represented using I, and linear combination of those two will always fall in this space. A base set of vectors I and j are the standard basis for a two-dimensional space. Consider three vectors I, j, k in three dimensions. Consider z here. So I cannot be represented j and k, j cannot be represented using I and j, and so similarly k cannot be represented using I and j. They all are independent in nature, so that I, j, k is a standard basis for a three-dimensional space. So keep these 2 points in your mind. Consider the one more example. The collections I, there are three vectors I plus j and 2j is not a basis for R2. Although it spans R2, it is not linearly independent because this is a vector. It can be represented using I here, I and j. So that example for this is 1 2 3 4 and 2 4 and 3 6 and 4 8. Right. So what is the basis for this? The basis for this is only 1 2 and 3 4. Only these two, because the remaining these three vectors can be represented using first vector. This is 2 times the first, this is 3 times the first, and this is 4 times the first vector. The basis for this is 2 and 3 4. All right, so next we do discuss the echelon form. Echelon form means that the matrix is in one of the two states: row echelon form and reduced row echelon form. Echelon form and row echelon form are one another same in general. Slight difference between a reduced row echelon form and a row echelon form, that will be discussed. So this means that the matrix meets the following three requirements. To say that the given matrix is in a echelon form, then following three conditions should be satisfied. The first number in the row is 1, so that one is called as a leading coefficient here. Every leading one is to the right of the right above it, one above it. The third condition is any non-zero rows are always above the rows with all zeros. Let us consider an example here. So it has two rows and three columns. The first condition is if we want to say that this matrix in echelon form, these three conditions should be satisfied. The first number in the row is 1. In the first row, the first number is 1. Yes, it is okay. And in the second row, first number is 1 here. These are zeros, it cannot be considered. It is called as a leading coefficient. It should be non-zero. In a second row, the leading coefficient is 1. So zeros are not considered as a leading coefficients. So the first condition is satisfied here. Second condition, every leading one is to the right of the one above it. For the first row, this principle is not applied. For the second row, the leading coefficient should be always right of the leading coefficient above to it. You can consider here the leading coefficient of second row, it is right to the leading coefficient of first row. You can observe here. So any non-zero, third condition, any non-zero rows are always above the rows with the all zeros. Here the third condition is not available here. That is, the third condition is if it has a 3 cross 3, and if non-zero rows, can we call this as a non-zero rows because one is available in the row. It should be above the 0 rows. All right, so consider the second example here. First row, it should have a leading coefficient, that is 1. Yes, it is there. Then second one, the leading coefficient should be 1. It is there, and it is right of the leading coefficient above to it. And any non-zero, if it has any non-zero rows, it should be above the 0 rows. That above the 0 rows is not available, so here we don't have any problem. Then consider the third example. Leading coefficient should be 1, and at the end it is having zeros, and it is having the zeros, and we can call this as a non-zero rows, and it should be above the 0 vector. That is condition. Okay, 3 rows, leading coefficient should be 1, leading coefficient should be 1, leading coefficient should be 1. Okay, second condition is leading coefficient should be right of the leading coefficient above to it. Yes, it is there. So for this value, it is available to the right of a leading coefficient of above row. It is available to the right of leading coefficient to its above row. As it is there. Okay, Let us consider a 4 matrix A, B, C and D. So you cannot say that a matrix A is in echelon form because the third condition is not satisfied here. Any non-zero row are always above the rows with all zeros. You can see the third row. You can see the third row. It is a non-zero. It is a non-zero row. It is not. It is not there. Below it, zero row should be there. So if these two are exchanged, then you can say that it is echelon form. Now it is not echelon form. Okay, matrix B, the second condition is not satisfied. See here, this one should be right of the leading coefficient of the row above it, but here the leading coefficient of above row is here, so it is there at the left side, so that matrix B is not echelon form. Matrix C, it is also not in echelon form because in second row the leading coefficient is 2, but it should be 1 according to the rule number 1. And D is also not a echelon form because the leading coefficient is -1 in second row, because it should be 1. So that A, B, C and D, they are not a matrix which are in echelon forms. So what is uniqueness of a echelon form? The echelon forms of a matrix, it is not a unique, which means there are infinite answers possible when you perform the row reduction. But what is a reduced row echelon form? Reduced row echelon form is different from the echelon form. There is a slight difference between echelon form and a reduced row echelon form. So we can have a multiple answers for echelon form, but a unique answer for a reduced row echelon form. What is that? Let us see. A reduced row echelon form is at the other end of the spectrum. It is unique, which means row reduced on matrix will produce the same answer no matter how you perform the same row operations. The conclusion is echelon form can have a multiple answers, but reduced row echelon form will have a unique answers. Let us see what you mean by a reduced row echelon form now. Reduced to what is row echelon form that we have discussed? A matrix is in the row echelon form if it meets the following requirements. Let us we are revising the same thing once again here. The first non-zero number from the left is always to the right of the first non-zero number in the row above. Row zeros, if all the zeros are at the bottom of the matrix. So technically what they are saying, a leading coefficient should be 1. In some books they are saying a leading coefficients can also be other than 1. That is the definition, but we do follow here we do maintain the leading coefficient as a 1 only. Now what is the difference between the row echelon form and the reduced row echelon form? If the leading coefficient in each row is only a non-zero number in that column, then matrix is said to be echelon form, zero echelon form. That is the difference here. You can consider here it is a row echelon form. Actually it is not a row echelon form because a leading coefficient in row number 2 is not 1, it is 2 here. Consider one more example. It is echelon form as well as the reduced row echelon form because it is satisfying the leading coefficient in all the rows should be 1. Yes, it is there. Then these values leading coefficients should fall to the right of the leading coefficient above to it. Yes, it is there. Along with these three conditions, there is a one more conditions. What is that? If the leading coefficient in each row is the only non-zero number in that column, here it is the leading coefficient of this row 1, it is the only element, in column number 1. So this one is a leading element in a second row, and also only a element, only a non-zero element in column number 2. Similarly, the third leading element, it is a leading element in third row, and it is a only non-zero element in a third column. Then if it is the case, then we can say that it is called as a reduced row echelon form. You can observe here. That will be the difference between row echelon form and a reduced row echelon form. Okay, that is, let us we discuss here. Reduced row echelon form is a type of matrix used to solve systems of linear equations. Reduced row echelon form has four requirements. The first non-zero number is in the first row should be 1. The second row also starts with the number 1, which is further to the right than the leading entry in the first row. For every subsequent row, the number 1 must be further to the right. The leading entry in each row must be the only non-zero number in its column. Any non-zero rows are placed at the bottom of the matrix. So they are not in echelon form. Some of the examples are given here. It is not in echelon form. The reason is the leading coefficient in third row, it is not to the right of leading coefficient in a second row. It is to the left, so that it is not echelon form. And a leading coefficient in third row, it is 5, but it should be 1, so that it is not in echelon form. And leading coefficient in second row, it is 2, but it should be 1. And you can observe here, leading coefficient in row number 1 should be here, or else a leading coefficient in row number 2 should be right of the leading coefficient above to it, but it is left side, so that it is not. And similarly, always in row echelon form, 0 row should be there at the bottom. It is a 0 row, it should be there in a 0 bottom, but it is not in the bottom side, so that it is not a echelon form. And what is the difference here in this vector? So the leading coefficient is -1, so that it is not in a echelon form. And what about this? It is also having a -1, right? Now they are in echelon form. These vectors are in echelon form, but not in reduced row echelon form. Let us consider here. Yeah, first leading elements. Okay, it is in echelon form. Echelon form. Yeah, this is also echelon form. It is satisfying all the conditions. They are right side, and leading coefficient is 1, and so on. So all fours are in echelon form, but not a reduced row echelon forms. So the meaning of it is to say that this is in reduced row echelon forms. Instead of 2, it should be 0, because in a row where a leading coefficient will occur, then corresponding column should have only a non-zero element here, but it is having 2. If it is 0 means, then we can say that a reduced row echelon form. And similarly, you can see here, it is echelon form obviously, but not a reduced row echelon form, because the corresponding column should have only leading element as a 0, only leading element as a non-zero element. But in this column, 3 is also available, so that if it is 0, then you can say that it is a reduced row echelon form. Some of the examples are given here. Yeah, so it is a echelon form as well as a reduced row echelon forms. Leading element in a row and in a corresponding column, it is the only non-zero element here. It is the only non-zero element, and it is the only non-zero element. So it is the only non-zero element. Okay, so I think I hope you have understood that what is the meaning of echelon form, row echelon form, and reduced row echelon forms. They are it is very important concepts used to solve null space and column space of a matrix. Next, a small concept, a pivot. Pivot position in a matrix A is the location in A that corresponds to the leading one in the reduced echelon form of A. Pivot column is a column of A that contains pivot position. Consider here. What is a pivot positions? What is a pivot position? So pivot position of this matrix is above the zero. These two are pivot positions. What are pivot positions of this matrix? This one, and this one. They should be there above the zero values. And what are pivot positions of this? It should be a pivot position. It should be a pivot. To this one, we should find a zero to its left and a right angle. Okay, so this is 1 2 3 4 5 6. For 6 columns we do find 3 pivot positions, 1 2 3. You can observe the position of these 3, uh, and it should have 0 at this position and this position. If these two are 0, then you can say that this one is a pivot, but it is not, because one to this right left side we have found 1, so that it is not a pivot position. So what could be the pivot position for this? I think only this one, and other than this one you don't find any pivot positions. All right, these all concepts are needed, we see in the next video. So like, share, comment on the video, and don't forget to subscribe the channel. We see in the next video. Thank you.